Okay, so let's take a look at this problem. It says the lifespans of a species of fruit fly have a bell-shaped distribution with a mean of 33 days and a standard deviation of 4 days. Now, the bell-shaped part is going to be important for part B. Okay, so let's take a look at part A first. The lifespans of 3 randomly selected fruit flies are 34 days, 30 days, and 42 days. Find the z-score that corresponds to each lifespan and determine whether any of these lifespans are unusual. Okay, so we're going to convert all 3 of those scores to z-scores and then see which, if any of them are outside of 2, either -2 or +2. Okay? Okay, so first, okay, we're told, is this working? Okay. We're told that the mean is equal to 33 days. Okay, they don't live very long. And a standard deviation is equal to 4 days. So our first value that we're given is 34 days. So we're going to find the z-score for 34 days. Okay, so this z-score is going to be, remember the formula is your x value minus the mean divided by the standard deviation. Okay, so this guy, of course I'm out of lead. Sorry. This one may not make it to the course. Okay, so I'm going to take 34 and subtract the mean and divide by 4. Now, one of the most common mistakes I see with converting to a z-score is having these values switched. Okay, so remember it's your x value first, then the mean, and then divide by the standard deviation. So that's equal to 1/4 or 0.25. Now, is this considered an unusual z-score? No. It's fairly close to the mean. Okay, look at these two values. They're fairly close together. Okay, but when we standardize it or convert to a z-score, we'll see that it is actually relatively close to the mean. So this is not an unusual z-score. Okay, so now let's find the z-score for, what's next? For 30 days. Okay, so this z-score is going to be 30 minus the mean of 33 and divide by the standard deviation. Okay, so what is that going to be equal to? Yeah, -3/4 or -0.75. Okay, so is this an unusual z-score? No, it's below the mean. This poor little guy didn't even live to be average. Okay, but it's not unusually low. Okay, so again, not unusual. Okay, last but not least, what do we have? 42 days. Okay, so again, we're going to convert to a z-score. So it's going to be the observation minus the mean divided by the standard deviation. Okay, so what is that? 2.25? That's 9/4, right? So that's 2.25. Okay, so is this an unusual score? Yes, it's unusually high. Probably someone just ended up swatting him. He's lived too long. Okay, so this one's considered unusual because it's outside of 2 standard deviations from the mean, okay, above the mean in this case. Okay, so that's not the tricky part. The tricky part for students tends to be part B. Okay, so let's take a look at what part B is asking. Okay, so it says the lifespans of 3 randomly selected fruit flies are 29 days, 41 days, and 25 days. Using the empirical rule, find the percentile that corresponds to each lifespan. Okay. Now remember the empirical rule from section 2.4 is the 68, 95, 99.7 rule. Okay, that's why they have to say the lifespans are bell-shaped, because the empirical rule only applies to bell-shaped data. Okay, so what I'm going to do is I'm going to sketch what's given. Okay, I know the mean is equal to 33 days with a standard deviation of 4. Okay, and I'm also told that it's bell-shaped. Okay, so we're going to use the empirical rule. Okay, so remember the empirical rule is the 68, 95, 99.7 rule. And that rule reads from the center out. Okay? But a percentile reads cumulatively, essentially from negative infinity up to the score in question. Okay, so we have to orient ourselves first by sketching the empirical rule and then read cumulatively from left to right. Okay? Okay, so let's sketch what's given. Okay, we're given that it's bell-shaped. Okay, pretend this is a bell. And I'm going to put the mean right in the middle. The mean's 33 days. Okay, so if I go one standard deviation above the mean, what score will that be if I go one standard deviation above the mean? 37, right? Okay, it's the mean plus one standard deviation, right? So if I go one standard deviation below the mean, what do I have? 29? Okay, so 29. So the empirical rule says that 68% lies between one standard deviation of the mean. Okay, so the empirical rule reads from the center out. Okay, so they want to know what's the percentile that corresponds to 29 days. See, that's the first one, right? Okay, so percentiles read left up to the point in question. Okay, we have the information from the center outward, but the percentile reads cumulatively this way. So we want to know how much cumulative percentage or cumulative area is that? Well, how much area is from basically negative infinity up to the mean? Okay, if I look at the half of the bell, how much area is that? 50%, right? This whole thing would encompass 100% of the data under the curve. Okay? So what I'm asking for when I'm asking for a percentile is I'm asking for this portion. Okay? But I know this. So I'm going to have to find this piece indirectly. Okay, so how much percent of the data falls between 29 and 33? Think of this by symmetry. Not 25. If this is 68%, right, 34. So 34% would be here, and another 34% would be here. Does that make sense? Okay, so given the fact that half of the data will fall between negative infinity, even though that really doesn't make sense with respect to the context of the problem, technically this goes on forever in the negative direction. Okay, so I have 50% falling all the way from the left up to 33. So I'm going to take 50% and I'm going to subtract out the portion I don't want. What do I don't want here? The 34%. Do you see that that will give me the shaded portion? Does that make sense? So I've used the empirical rule, but I've had to manipulate it. Instead of reading from the center out, I'm reading from the left up to the point in question. Okay, so that's going to be equal to 16%. So 29 days corresponds to the 16th percentile. Okay, does that make sense? All right, so the hard part is done. Now we just need to do that same thing for the other two. Okay? Okay, so looking at the 41 days, is that above the mean or below the mean? That's above the mean. So I'm going to go how many standard deviations I need to until I reach 41 days. Okay, so I know one standard deviation is 37. If I add 4 to that, then what do I get? I get 41, right? Okay, so if I go 2 standard deviations below the mean, and then subtract another 4, this would be 25, correct? Okay, so what does the empirical rule say? How much data falls between 2 standard deviations? 95%. Remember, it's a 68, 95, 99.7. So that would be 95%. Okay. All right, so what I'm looking for when I'm talking about a percentile is I'm looking for the total cumulative percentage from negative infinity up to this point, which would be 41. Okay? Now I know 41 is not the 95th percentile because I have this little smidge down here, right, that I have to include in this. Okay, this is like a running total. Okay? Okay, so to get the area, okay, I have to figure out how much is in this little tail here. Okay. There's a couple ways to do this. Okay, one way that I'm looking at is if 95% of the area falls between 25 and 41, by symmetry, how much area has to be in each of these little tails? 2.5%, right? Because 100% of the area is under that curve. Okay, does that make sense? And so breaking it in half, I've got 2.5% here and 2.5% here. But I don't want this area here. I'm doing a running total. So the percentile is going to be 2.5% plus 95%. Okay, so what's that going to be equal to? 97.5%. Okay, so 41 days corresponds to about the 98th percentile. Okay, or you just need to round the way you're told to in the homework. Okay, so it is the 97.5th percentile, but 98 percentile is easier to roll off the tongue. Okay, so does that make sense? All right, so let me stop recording.